Okay, so in last class, we talked about the important components of internal combustion engine. And in today's class, we are going to look at how to design some of those components. So the main component, they are piston, cylinder, connecting rod, crankshaft, valve assembly, and so on. So let's start with the design of cylinder. Now, depending upon the type of engine, whether it's a 4-stroke engine or a 2-stroke engine, whether it's a diesel engine or a gasoline engine, there could be slight variations in the design process. But overall design procedure is going to remain the same. So I'm going to first give you a step-by-step recipe for design, and then we will work out a problem. So let's look at design of cylinder. Now cylinder provides a combustion chamber, sort of, it's a cylindrical piece, and the piston slides back and forth inside the cylindrical piece. So first and foremost, what we want to find out is we want to find out what is the thickness of the cylinder wall. So if you look at the cylinder, and I'm going to show you the way the cylinder looks. This is the cross section, cut cross section. So you can think about like a Coke can that is cut into two pieces, two halves. So, and we are interested in finding out the thickness of the cylinder. Which is T. Now, if you look at design of the thickness, you are going to have two types of stresses. And I want to give you a simple example. Think about, you have a Coke can. So this is a Coke can, okay? And I don't know if you have done this exercise, but for some reason, you keep this Coke can in a freezer. So next to all these ice cubes. What's going to happen is the liquid, which is here, that is going to freeze. After the liquid is frozen, it becomes ice. It starts expanding. And most likely, you will notice that when you open your freezer door, the Coke can has cracked and all the liquid has sort of little bit splashed around. That happens because as the liquid expands, as you know, for water, when the water temperature is about 0 degrees, it starts actually expanding. So what happens is the ice sort of increases the pressure inside, and because of that, the can cracks. Now you will notice there are two ways this can potentially crack. So think about it like this can, the top of the can sort of separate out from the bottom of the can. This is one potential failure. And the second failure is basically you see a crack in the longitudinal direction. So these are two different types of stresses that are possible. Most likely, you will observe the crack that runs along the longitudinal direction. So if you look at the failure of a cylindrical object that is pressurized, that is considered as a pressure vessel design. So if you look at the cylindrical object and that internal has pressure and the pressure increases, there are two types of stresses that are generated. One is a longitudinal stress, And the second is circumferential stress. So you have these two types of stresses. The one thing that we need to observe, that if you look at the way the failure is happening, the way the stresses are acting, these two stresses are perpendicular to each other. So these stresses are perpendicular to each other. Now, what happens is, so if you think about the piston is somewhere here. And this piston, there is this piston pin, and then there is this connecting rod. This is piston pin, this is connecting rod, and this piston is going to go up and down or back and forth inside the cylinder. If you think about it, because of the articulation of the piston, as the piston is being articulated, you can observe that there is some side thrust. So there is going to be some sort of side thrust. But this side thrust is usually slow, so we ignore it. So what we do is we actually ignore that side thrust, teeny tiny amount of side thrust, and then what we do is we try to find out the pressure inside this cavity. So this is the pressure here. And this inside pressure is the design quantity. So for gasoline engine, this design pressure is typically lesser than the diesel engines. So I'm gonna say P is the maximum pressure, is the max pressure inside cylinder. And I'm gonna say DO, which is the outside diameter of cylinder. D is the inside diameter of the cylinder. And T, I'm gonna call it the thickness, wall thickness. And 1/m, as you know, this is the Poisson's ratio, which is the lateral strain divided by longitudinal strain. And typically, this Poisson's ratio value is in between 0.2 to 0.3. So you can take it as 0.25. Now, I'm going to give you the expression for the longitudinal stress. And this equation is valid for all thin-walled cylinders. So longitudinal stress is equal to force divided by area. And the force is, if you think about the inside diameter is nothing but the diameter of the piston. So the inside diameter of the cylinder is nothing but the outside diameter of the piston. So it's going to be pi/4 times d square times p. This is the force divided by pi/4. Then you have d outside square minus d square. So this equation gets simplified to d square p divided by d outside square minus d square is equal to sigma L. And this is the expression that we will use for the longitudinal stress determination. And this will be one of the design equations that we will use. Now, if you look at the circumferential stress, so circumferential stress is given as sigma C. And this circumferential stress is given as D times L, which is the length of the cylinder, multiplied by P, which is the pressure, divided by 2 times T times L. Now, a quick description of this circumferential stress. What I want you to do is, for a minute, I want you to look at the cylinder sort of in a cut section. So think about the cylinder sort of that is cut, which is like this. And the pressure is acting over here, everywhere. Pressure is always going to be perpendicular to the surface. So if you look at the total area, that will be the projected area. So I'm going to draw this projected area. So this pressure is going to act on this projected area, that is D, and this is the length of the cylinder, which is L. So the total force is equal to, the total force will be P, which is pressure, multiplied by D multiplied by L. Now, if you think about the area that is resisting the failure, the area that is resisting the failure is this area. This is this area. And if this is thickness T, then area is equal to 2 times T times L. So this is the area and this is the force. Now what I'm going to do is, I'm going to use the Poisson's ratio relationship, because if you think about it, this is sort of a biaxial stress condition. So what it means is you have two stresses on an element that are perpendicular to each other. So what's going to happen is, due to the Poisson's ratio relationship, a component of longitudinal stress will act in the circumferential direction, and component of circumferential stress is going to act in the longitudinal direction. So this is an important observation. So sigma C and sigma L will be perpendicular to each other and act simultaneously. So this leads to biaxial stress condition. And once again, what it means is the component of longitudinal stress will be in the lateral direction or the circumferential direction, and component of circumferential stress is going to be in the longitudinal direction. And I'm going to give you the expression. So this is called as apparent or total longitudinal stress, or actually this is called as the net. So this is called as the net sigma L. So this is the total longitudinal stress, is the sigma L that we calculated minus sigma C divided by M, and net sigma C is equal to sigma C minus sigma L divided by M. And if you think about it, in the very first class, we kind of looked at this example wherein you have a rod that is loaded in the axial direction. Because of the loading in the axial direction, there is going to be stress in the lateral direction. But visualize for a second that this rod is also pulled in the lateral direction. So P2, P2. So what would happen that because of this lateral pull, you are going to get some stress in the longitudinal direction. And that is something that you need to keep in mind when you are designing the pressure vessels. So a quick suggestion on the side. If you are going to design a pressure cooker, say for an example, or if you want to design a boiler where the thickness or the wall thickness is significantly lower than the diameter, that is called as a thin walled pressure vessel. And this process would be the same in the case of thin walled pressure vessels. And as you will see that if you are trying to design maybe an air pump, then the same phenomenon, same concept will be used. If you are going to design, say, a cylinder for the compressor, air compressor or a gas compressor, same process is going to be used. So remember these equations, because these equations, they remain the same, even though the application may be slightly different. Now, what we are going to do is we are going to determine the thickness of the cylinder wall using this formula. T is equal to P times D divided by 2 times sigma C plus C. So this equation will be useful. And if you look at the way this equation comes about, that this equation is derived from this sigma C expression. So you have D times P divided by 2 times sigma C gives you the thickness. Now, what is this C? Now, this C is called as reboring allowance. So I need to write this down and I'll explain what is reboring. C is called as reboring allowance. So sometimes what we try to do is we try to over design. And the reason for that is these engines, when they are designed to last for, in the case of automotive engines, 250,000 miles. In the case of marine engines, something similar, they measure in terms of nautical miles. Or if you try to look at the generator, they are supposed to last for maybe 15,000, 20,000 30,000 hours of continuous operation. So what happens over the period of time? The piston and the cylinder assembly starts wearing out. So piston that is reciprocating inside the cylinder, it starts sort of pitting the cylinder surface. So you will see small, teeny tiny scratches. And initially those scratches may not be visible, but over the period of time, those scratches, they deepen. Or sometimes there are some impurities in the fuel and that may not be visible to us. But those impurities sort of get impinged on the cylinder surface, they scratch it. And after some time, you will notice the engine would lose efficiency. Engine would lose power. Engine would start smoking. So in that particular case, or sometimes what would happen is it could lead to lubrication failure and the piston cylinder assembly would just slack. In other words, piston would jam inside the cylinder. So at that time, what they do is they actually have a boring machine. So if you look at, and I would encourage you to look at the boring machine, what they do is there is a boring machine and they take out, if you look at this cylinder, they take out some material from the cylinder, inner cylinder. So in other words, they bore the inside diameter of the cylinder. And what is the purpose of this reboring? So what happens because of reboring is the surface is smoothened out, and then what they do is they replace the piston, replace the piston rings, and your cylinder piston assembly is as good as new. Sometimes if significant amount of reboring is required, what they do is they rebore and then they put a liner inside the cylinder. And now initially the cylinder did not have a liner, but it got worn out. And then what you do is you basically add a liner. Now, why is this all jugglery needed? Because many a times, and this is important, many a times this cylinder is part of the cylinder block. It's not an isolated component. So if you look at a complete engine, and I'm going to show you sort of, so if you look at an engine, you will have aluminum cylinder block, and these cylinders are bored inside this solid hunk of aluminum, or it could be cast steel, or it could be any material. So rather than replacing the entire block because there is a piston cylinder slab, it's easier to just remove the piston, bore this uh, cylinder and put a liner or a new piston and get the whole assembly running. That saves a lot of cost. Many a times, some engines are so huge. So for an example, if you look at the marine engines, and I would encourage you to take a look at picture of the marine engine. So it's like 8 or 9 feet tall engine. So think about the amount of material that someone would need if the piston or cylinder needs to be replaced. So what they do is, in that case, you add some additional reboring allowance just to compensate for some sort of machining that may be needed in future during maintenance. So, and this used to be very common in old engines, but nowadays with if you are particularly looking at automotive engines, the automotive engines reboring is not done very frequently unless the engine is super expensive or it's a custom engine. But many a times what they do is they find a reworked engine or refurbished engine and they swap the engine. So this is something to keep in mind. So next thing is what I want to talk about here is, so pressure P will be given to you. It will be given. And then this diameter would be designed, or it would be dependent on the design parameters, or this diameter could be considered as the outer diameter of the piston. So this is the same as dia of piston. However, the value of sigma c, which is the circumferential stress, it will vary all the way from 35 Newton per millimeter square to 100 Newton per millimeter square. And it totally depends upon the size and the material of the cylinder. And when we look at the actual example, it would be clear. So depending upon, and this C, this reboring allowance, that depends upon the diameter. So for an example, you have D and you have C. So for an example, if your diameter is 75 millimeter, the reboring allowance is 1.5. If your diameter is 100 millimeter, the reboring allowance is 2.4. So we will use the design data book, actually table 32.1, to find out what is the value of the reboring allowance. And depending upon the application, you will observe there is a wide range in the cylinder wall thickness. So for marine engines, the cylinder wall can go all the way up to 50, 75 millimeters. For automotive engines or for small weed whacker engines, it can go as low as 4 millimeters. Alternatively, there is an empirical relation I want you to take a note of. This thickness, and this comes from the experiments and the empirical thumb rules. So D plus 1.6 millimeter. So this is just an empirical relationship. So even if you use this relationship as a check, we have to use this equation to make sure that the design is safe. So this is something important. Now, sometimes you want to add a water jacket, or sometimes you just use a dry liner. So in the dry liner, the water is not in contact with the liner. So thickness of the dry liner So I made a mistake here. Dry liner is 0.03 times D, which is D is the diameter. If you add a water jacket, so in other words, you add a manifold or you add internal holes inside the cylinder block so that the water can flow around the cylinder, then that is typically considered as thickness of the water jacket. And thickness of the water jacket is 0.032 D plus 1.6 millimeter. And you can add additional space between the outer cylinder wall and the inner jacket. So if you think about, so let me draw what we are talking about. So this is the cylinder, and what you have is you have some openings. So this is the cylinder, and think about that this cylinder is part of the whole cylinder block. So there is this cylinder block, and there could be second cylinder here and so on. So this, the water is going to flow from here, come out from here. So this thickness of the water jacket is nothing but the the thickness, this thickness. But it is also important that you want to maintain certain distance from the outer wall. This distance is the distance from outer wall. And that is usually taken as about 10 millimeters to 5 millimeters, 10 millimeters to 5 millimeters, depending upon the spacing. Now, the next part is bore and length of the cylinder. So, bore is diameter and length of cylinder. Now, before we talk about bore and length of the cylinder, I would like to introduce an important concept, which is called as the break mean effective pressure. And let me ask you this question. And have you seen this concept before in thermodynamics? Break mean effective pressure. You can give me a thumbs up or thumbs down, or put your comments in the chat window. Have you seen break mean effective pressure or studied break mean effective pressure? So what is, no, okay, so good. So what is this break mean effective pressure? Now I want you to understand for a second, think about the piston cylinder assembly. Think about the piston cylinder assembly. And we saw the PV diagram. We saw this PV diagram. We looked at PV diagram for Otto cycle, which is the gasoline cycle. In that case, you have constant velocity and constant volume heat addition. And we saw this cycle to be something like this. You would observe in this cycle, the pressure is continuously changing. So in other words, the pressure inside the cylinder, the pressure here, this is the pressure. This is continuously changing depending upon whether it's a suction stroke, compression stroke, a power stroke, or expansion stroke, and exhaust stroke. So what we do is we try to find out sort of an average pressure across the entire cycle. And I want to give you sort of a thermodynamic explanation for this. So think about the work done. Think about this work done, which is area. And then if I were to find out an average pressure, so if I were to find out a P average, and this is the stroke volume, Vs. And please note, this is stroke volume. This is stroke volume. So if I were to find out the average pressure, that is called as, in terms of internal combustion engine design, it's called as mean effective pressure. So first and foremost, this is called as mean effective pressure, which is called as MEP. Now, in the last class, we talked about different types of losses that happen. So quick recap. So we have chemical energy. So I'm going to call this chemical energy, that after combustion that gets converted to mechanical energy. And this mechanical energy is used to drive a piston forward. And then there are some frictional losses And those after those frictional losses, so there are some chemical losses or energy losses, combustion losses. So I'm going to say combustion loss. Then here there is some friction loss. And at the end, what you have something called as brake power or brake energy, or I'm going to call this brake power just to be consistent. So I want you to understand, if you were to look at the pressures at the end of combustion, at the age of combustion, so you can actually construct this diagram for the mechanical energy, which is over here. You can construct this type of diagram for the brake energy, which is over here. So in other words, you can find out the average pressure or mean effective pressure that is acting during the mechanical energy conversion. You can find out the mean effective pressure that is acting during the brake power generation. So there are two pressures that I want you to understand here. So there is called as indicative power, and there is something called as the brake power. So what is the difference between indicated power? Indicated power minus friction loss is equal to brake power. Now, if you look at the specifications for internal combustion engine, or for that matter car, they will always specify the brake power or brake horsepower. Why is we are interested in brake horsepower? Because we don't really we are not really concerned about what is the actual power that is developed inside the engine. What we are interested in, what is the power output I get at the axle or at the wheel. So I'm not really interested in uh, the actual power that is generated inside the engine, but I'm interested in the power here. So power, this is the brake power, because that is the power available at the brake. Or if you were to put this vehicle on a dynamometer, that is what you would measure. But here is something that I want you to understand. Brake power is going to be less than the indicated power. Indicated power is actually the power that is generated after chemical to mechanical energy conversion. So here there is this chemical energy, and here there is this mechanical energy. So after combustion, chemical energy got converted to mechanical energy, and this is where the pressures are going to be maximum. So if you were to calculate mean effective pressure, and what I mean by that MEP, if you find out mean effective pressure for indicated power, it's called IMEP, which is called indicated mean effective pressure. And sometimes if you find out mean effective pressure using the brake horsepower, so that is called BMEP, which is brake mean effective pressure. So brake mean effective pressure is less than indicated mean effective pressure. But indicated mean effective pressure is the pressure that we should be concerned about when we are designing the piston cylinder assembly, because that is the maximum pressure that could occur inside the piston cylinder assembly, and that pressure is generated after the combustion. Now, here is an interesting question for us to think about. So we talk about that this indicated mean effective pressure or brake mean effective pressure. This is sort of an average pressure that is calculated, that is acting in the cycle. Why not? And some of you may ask this question, and as a design engineer, you should. Why not? We look at the maximum possible pressure and then find out the cylinder dimension. To answer that question, yes, certainly, if you want your engine design to be super bulky, if you want to over design your engine, by all means, we can go ahead and we use the maximum possible pressure. But if you think about it, the maximum possible pressure is going to be in the cycle for a fraction of a millisecond. So effectively, your indicated mean effective pressure or brake mean effective pressure is going to act on the cylinder. And that is the reason why we don't consider the maximum pressure, but we look at indicated mean effective pressure. Now, I want to give you some guidelines here just for your reference. So if I were to say PM is equal to indicated mean effective pressure, and I'm going to call it IMEP. So this is the average pressure after combustion, and we want our cylinder to be strong enough to withstand this pressure all the time. If I were to say D is the bore diameter, bore means inside diameter, this is called as bore, this is diameter D. And clearly A is equal to pi by 4 D square, which is the area. And if L is the stroke length, and stroke length is 2 times crank radius. So what is the stroke length? So stroke length is the distance between the top dead center and the bottom dead center. So this is the stroke length. So this is how much the piston is going to travel in each cycle. Now, depending upon whether we have 4-stroke engine or 2-stroke engine, remember in 4-stroke engine, 2 cycles are needed to complete, or 2 revolutions. Let me write this down. 2 revolutions to complete revolutions. 2 revolutions. 2 revolutions per cycle. In 2-stroke engines, 1 revolution per cycle. So if I want to find out, N is equal to number of working strokes per minute for 2-stroke engines, it is N, and for 4-stroke engines, which is N by 2. Where N is the speed in RPM. N is the speed of engine, RPM. So if you have a 2-stroke engine running at 1000 RPM, that means your working strokes are 1000 strokes per minute. On the other hand, if you have the 4-stroke engine again running at 1000 RPM, then you have effectively 500 strokes per minute. And one thing that you have to be absolutely clear, that engine misfire is an undesired condition. So you don't want cylinder misfiring, because what happens is, if the cylinder misfires, then the flame front, rather than helping us, it hurts us. So it actually immediately, if the cylinder misfires, then you would notice sudden drop in the power. Not only that, you will also notice that the engine would start vibrating. Most likely, if you have an ECU or an automotive engine, your check engine light will come on. Not only it will come on, but it will start blinking, because this is the condition where you need to stop the engine, because that will create severe damage to the engine. Sometimes engine misfires are possible because maybe the fuel is contaminated or cylinder temperature is too high, and that is where its EGR valve, exhaust gas recirculation valve, comes in the picture. So if for some reason there is fuel variation in the fuel quality, or for some reason the temperature of the cylinder goes higher, say it has insufficient amount of coolant, and the the temperature of the cylinder goes up, then what happens is you have something called as the exhaust gas recirculation EGR valve. That EGR valve would open, and it will mix the burnt spent gases with the incoming charge to reduce the quality of the incoming charge. What would happen when the quality of the incoming charge is reduced? That means you will not reach the pressures that you would reach actually, in ideal case. Your mean effective pressures would be low. Lower mean effective pressure means your power will be low, but that will drop your cylinder temperature down immediately, and that may prevent cylinder and piston from burning or overheating. And if that is, again, that is a very small intervention. If that continues, then your temperature gauge would go, it will redline. And then if it continues to be in the red line, your check engine light will go on and it will start blinking, indicating that this is uh, injurious to the health of the engine, and you should immediately stop and get the engine checked out. So there are small techniques that we see or we adapt to make sure that the engine is operating at the optimal temperature, because that optimal temperature range is quite limited. If the engine is running at lower temperature or the engine is running at a higher temperature, the combustion is not going to be efficient. Okay, so next, moving on, let's look at how do we find out the bore and the stroke. So for that, the important design parameter is indicated power. And I want to give you the definition of indicated power. It is the maximum mechanical power available in engine. So what it means is, after combustion, the chemical energy gets converted to mechanical energy, and this is the maximum mechanical energy or mechanical power that is available. And we want our engine hardware or engine components or cylinder, piston, everything, all sub assemblies, to be able to sustain this indicated power. And if you look at the equation for the indicated power, IP is equal to PM, which is the indicated mean effective pressure, times L multiplied by A multiplied by N divided by 60. And this is in watts. Sometimes indicated power is given in horsepower in some older design books. So if you come across the horsepower equation, then I would just convert that to kilowatts or watts and then work out the problem. Now, the next thing that is something important is if you look at this equation, there are two unknowns. So if you look at the diameter, that is unknown, and L is unknown. So we cannot solve two unknowns using one equation. So it is customary to consider the length of the stroke L is equal to 1.25 diameter T 2 times the diameter. So this is the relationship, and this is called as L to D ratio. L to D ratio of 1.25 to 2 is quite common. In the case of some special purpose engines, they are called the square engines. L to D ratio of 1 is also possible. So there are cylinders and piston assemblies where L to D ratio, I have seen L to D ratio as 1. But typically, L to D ratio can vary from 1.25 to 2. Now, usually you have clearance on the both sides on the cylinder. So to compensate or to account for clearance, the length of the cylinder L is considered as 1.15 times stroke length L. So this is the length of the cylinder. So L, length of cylinder. Now I just want to give you one more expression. So as you know, indicated power minus friction losses is equal to brake power. So these are mechanical losses. So mechanical efficiency mechanical is given as brake power divided by indicated power, which is BP divided by IP. So sometimes when you look at the engine design problem, they will not give you the value of indicated power. They will give you the value of brake power. So brake power is equal to maybe 10 kilowatts. So what we have to do is we have to divide that brake power by mechanical efficiency. So 10 divided by efficiency mechanical to find out the indicated power. And indicated power and mechanical efficiency values are usually given. And if the mechanical efficiency values are not given, depending upon the design data book that you use or design guidelines, you can refer the table for a particular type of engine and it will give you typical mechanical efficiency powers. And one thing that you want to consider is over the period of time, mechanical efficiency decreases. So we will consider the engine as brand new, a little bit sort of broken in. And during that time, the mechanical efficiency is maximum. So we'll use the maximum mechanical efficiency for determination of indicated power, and we will use that indicated power equation into into the equation 1, which is on this slide. Now, just to add something to it, something to keep in mind is the maximum pressure, the maximum gas pressure. So maximum gas pressure is typically end of combustion is 9 to 10 times indicative mean effective pressure. So if somebody asks you, how would you find out the maximum gas pressure? So you would just multiply the indicated mean effective pressure by 10 times, and that should give you the maximum gas pressure. But one thing to keep in mind, that this maximum gas pressure is only for a fraction of a millisecond. So that is not the actual pressure that is going to act on the piston and cylinder assembly for the entire duration of cycle. Okay, any questions in the cylinder design so far? So next part is we have to design the cylinder flanges and studs. The design of cylinder flanges and studs. Now, what is this? So if you look at the piston cylinder assembly, the cylinder would usually, let's take a look at the single cylinder design. So we just have one cylinder, one piston. So you would see that you would have cylinder that is something like this. And on top, there is going to be a cylinder head. So here, there is going to be a cylinder head. And this cylinder head is going to have a particular shape that will form the combustion chamber. And between the cylinder head and the cylinder, there will be a gasket, a thin gasket. So many a times, if you go for servicing and you notice that engine is smoking, sometimes you will hear, or people would say, hey, you have a head gasket failure. So this is called as the head gasket. So what is the purpose of the head gasket? Head gasket is actually used for sealing so that the gases during combustion, they do not escape from the side. Many a times what happens is, if the engine is overheated, it's actually a very thin, soft metal gasket. So what happens is, sometimes the engine gets overheated and this gasket gets warped. And then you will observe that this doesn't seal the engine properly. And sometimes what you can do is you can scrape off the old gasket and put a new gasket, and engine may work. So the new gasket may seal it. Sometimes you will notice that the gasket has warped to such an extent that there are indentations on the piston, or indentations on the cylinder. And at that time, you have no other choice than to remachine the surface And that is very commonly done in automotive engines. And then actually you refit. So that they provide some clearance for machining the top. But so you have this cylinder flange. So this is cylinder flange. So this is flange. And then you're going to have the bolts. You're going to have bolts all around the cylinder. You're going to have bolts that will keep the cylinder head. This is cylinder head. Tightly secured to the cylinder. So how do we find out the flange thickness? So we can use some empirical rules. So typically the flange thickness is equal to 1.2 to 1.4 times thickness of the cylinder. So flange thickness is 1.2 to 1.4 times uh, the cylinder thickness. So this is called as, and I should write this down here. This is the flange thickness. Now the next part is what we want to look at is the studs. And think about the studs. So for an example, I just want to show you the top view. You're going to have the cylinder head, and on this cylinder head, symmetrically, there will be these studs. And the number of studs are dependent on the number of uh, bolts are dependent on the cylinder diameter and the bore. So the equation is these bolts should be able to withstand the force, the maximum gas force. So what we will do is we will say pi by 4 times d square times p is equal to ns times pi by 4 dc square times sigma t. So the bolts failure in tension. Now one thing I want to emphasize at this point is here this P is not the indicated mean effective pressure, but this is the maximum pressure. So we will, if we are given an indicated mean effective pressure, we'll multiply that by 10 times and design the bolts so that they are designed for maximum pressure. And now the question is why? Because if you think about it, the purpose of the bolt is not only to hold the cylinder head securely on cylinder, but also apply the clamping force so that it is effectively sealed. So in other words, there will be some torque specifications. There will be some additional requirements to maintain the proper seal between the cylinder head and the cylinder. So to account for all that, we would actually use the maximum gas pressure. So P is the maximum pressure and NS is number of studs that is 0.01 D plus 4. So usually you will notice typically you would have 6 to 8 bolts or studs. And why do we have 6 to 8? Because there is a reason for that. If you think about it, if I just have 4 bolts, 1, 2, 3, and 4. If I just have 4 bolts, if the power generated by that engine is very small, in other words, the pressure inside the engine is not very large, then probably 4 bolts would be sufficient. But what we want to make sure is not only the bolts are holding that head onto the cylinder, but the gasket, which is in between here, is applied a constant clamping force. So with 4 bolts, the clamping force variation may not be even, or it won't be symmetric. That's why typically I have seen anywhere between 6 to 8 bolts. And DC is the core diameter of studs. Once again, if you look at stud is nothing but sort of a bolt. And you will see that this bolt is like this, and here it's gonna be like this. So the innermost diameter is DC. So this diameter, innermost, is DC. And that is the diameter that we will look at. Now, one thing you want to make sure when you study the pressure vessel designs or when you study the boilers, there is something called as making sure the joint is leak proof. What it means is you want to ensure the optimal number of bolts so that this particular joint is sort of leak proof. So to ensure leak proofness, this pitch, there is a design guideline. It should be somewhere between 19 square root of D to 28.5 square root of D. And why is this required? Because think about it. If these two studs are very close to each other, then what's going to happen is you will have some sort of an overlap of and the pressure is not going to be uniform. If they are too far apart, then the pressure would be low. So this is basically sort of a design guideline that we can follow to make sure that the joint is leak proof. And the last part of the cylinder design is the design of cylinder head. And this is actually very straightforward. So design of cylinder head. Cylinder head. And it's like the only important parameter is the thickness of the cylinder head, which is D times square root of C P divided by sigma C, where C is the design constant, which is considered to be 0.1. Sigma C is the circumferential stress in the cylinder head that can go from 30 to 50 Newton per millimeter square. So this is the circumferential stress in head. And then P, once again, P is the max pressure. So P is the max pressure and D is the cylinder bore or inside diameter. And then the next question is, what is the pitch circle diameter? So what is this diameter? And this diameter is typically the bore diameter plus 3 times the diameter of the bolts. So this is the bolt or stud diameter. This is the bore. And this is pretty much the design of cylinder. We are going to take a break for 15 minutes, and after the break I will work out a problem. So I'm going to stop, I'm going to pause recording. I will see you at about 7:30. So let's look at a cylinder design problem. So design a cylinder for the 4-stroke diesel engine. So the brake horsepower or brake power is 5 kilowatts. Speed is 1200 RPM, and indicated mean effective pressure IMEP is 0.35 Newton per millimeter square, and mechanical efficiency %80. So 80%, 75 to 85 is the percentage of mechanical efficiency. So determine first bore and length, second thickness, and then size of the studs. So we have to design the cylinder. So what we would do is, step 1, bore and stroke design. So what I'm going to do is, I'm going to assume L by D ratio is equal to 1.5. And this is just assumption. You can use L by D ratio from 1.25 to 2. That's totally fine. One thing that you want to understand or take into account, that the brake power is given to us. So we need to know the indicated power. So indicated power IP is equal to brake power divided by efficiency mechanical. Brake power is 5 kilowatts. Mechanical efficiency is 0.8. That gives you indicated power 6280 watts. Indicated power is given as indicated mean effective pressure times L times A times N divided by 60. So 6280 is equal to 0.35 times L by D ratio is 1.5 to L is 1.5 times D multiplied by pi by 4 D square multiplied by N is the number of working strokes. So please understand, this is a 4-stroke engine. Since it's a 4-stroke engine, effective strokes is equal to speed by 2. So 1200 divided by 2, so 600. So I would encourage you to use your calculators and quickly solve this and tell me the answer. And the answer is 115 millimeter. L, small l, is equal to 1.5 times D. 115. So that is about 200 millimeter. Actually, it's made a mistake here. It is 1.5 times 115, and that is about 175 millimeter. Capital L, which is the total length, is 1.15 times L, which is 200 millimeter. Now, next step is we have to find out the thickness of the cylinder head. So next step, step 2, is the thickness of cylinder head. Now, maximum pressure is about 9 to 10 times the mean effective pressure. So the maximum pressure is 3.15 Newton per millimeter square. And the thickness of the cylinder head is D times C P divided by sigma T. So D is equal to 115, C is 0.1 multiplied by 3.15 divided by, and I'm going to assume sigma t is equal to say 45 Newton per millimeter square. So just the assumption. So this gives you about 10 millimeter. Step 3 is we have to find out the size of the studs or the size of the bolts. So we are going to use the equation. The force acting on the cylinder is pi by 4 d square times p, which is the force, that is pi by 4 115 square 3.15 . So this is the force, and I'm going to use number of bolts, studs or bolts is equal to 6. You usually have even number of bolts, so 4, 6, 8, 10, 12, and this force is equal to number of studs ns pi by 4 times dc square times sigma t. 6 65, and that should give you the value of d c is equal to 10 millimeters. And we need to find out excuse me, the pitch circle diameter. So the PCD of studs is D plus 3D is 115 plus 3 times this diameter is DC divided by 0.8, because D is the actual diameter, which is pore diameter divided by 0.8. So this becomes 157 millimeter. And the pitch of the studs pi times dp millimeter. And then you can check if the joint is leak proof. So for leak proof joint, pitch should be somewhere between 19 square root d and 28.5 square root d. So you will see this dimension is 71, this dimension is 107. So our dimension 83 is right in between. So which means the joint is leak proof. Any questions on this design? So the next part I want to talk about is how do we design the piston. So if you think about the piston, so we are going to talk about design of piston. And piston is actually sort of a disc that reciprocates inside the cylinder. And I just want to emphasize the complexities of the piston design. So if you look at the cross section of the piston, you will observe that you have some grooves for piston rings. Then you have additional groove for the oil ring. Then this piston is going to be symmetric. This is the center line of the piston. And internally, if you look at the piston is hollow, but its shape is unique in a sense that you will notice that there is some sort of a dip on the top of the piston. And this top of the piston and the cylinder head actually make the combustion chamber. Then you have this piston thickness. And then if you see here, there is this land, and then this is how the piston would look like. And usually the pistons, the simple pistons can be machined. For example, if you look at the weed whacker pistons or pistons for a very small engine, they can be machined on CNCs. But many a times the large pistons are typically cast and then machined. So you have additional ribs to strengthen the piston. And this is where you have the circlip and the piston pin actually sits here. So this is the piston pin. And what we want to do is we want to design the piston, and here are the important dimensions. The external diameter of the piston is same as the bore diameter. But what we want to do is, in addition to the bore diameter, we want to find out this thickness, T, thickness of the piston. And then we have to find out the dimension of the ring section. So this is the ring section. So this is where the rings are. This is the top land. And this is the barrel thickness. And this is another, so there is the bottom part of the piston. This is additional thickness, which is called T4. So in this exercise, we will try to find out the important dimensions of the piston. Now, the important part in piston design is heat dissipation. Because what you want to do is you want to make sure that there is tremendous amount of heat and forces that are acting on one side of the piston. So this piston is able to dissipate all that heat to the cylinder lining or oil. So we have to make sure that the cylinder and piston assembly does not warp. So typically you would see piston from the materials that have good coefficient of friction. So for an example, you can use aluminum pistons, you can use cast steel, cast iron. You don't usually use cast iron because cast iron is a brittle material and it cannot take shocks very well. But you can use alloy steel, or you can use aluminum alloy pistons. But important parameters that I want you to understand is this high heat conductivity is one of the important characteristics of pistons. If you look at the engines, which are slightly old engines and with a low power requirement, sometimes I've seen cast iron pistons to be used, but they have some additives or some sort of cast iron alloy that increases their toughness. So for different types of material, you have to make sure that the surface temperature of the piston is well within the specs so that the piston material does not plastically deform. So if you were to look at cast iron alloy piston, you want to make sure that the temperature is about 450 degrees C. Max temperature is about 450 degrees C. If you look at aluminum alloy piston, you want to make sure that the piston is about 200 or 300 degrees C. Aluminum piston are usually they are supposed to run at the lower temperature, because what happens is aluminum at very high temperature start losing their strength compared to the cast iron. So aluminum, that is the material property, that as the temperature increases, the delta drop in the strength for aluminum is quite high. So these are some type of guidelines that you want to follow just to make sure that the piston temperatures are well within the limit. So let's look at how do we design the piston assembly. So first and foremost, we will look at design of piston crown or head. Head, which is sort of the top part. So the important conditions for that are: one, strength, and second, heat dissipation. So we should be able to sustain the impinging gas forces. At the same time, it should be able to dissipate tremendous amount of heat that is generated in the combustion process. So if you think about the design, there is something called as the Grashof formula that is used for the thickness of the piston head. So I'm not going to derive this formula, but I'm just going to give you the expression. So TH is equal to three times P times D square divided by 16 sigma T. Now P is the maximum pressure. D is equal to the bore diameter. Sigma T is the tensile strength. And this strength could be material dependent. So for an example, if you have cast iron, and depending upon whether you have gray cast iron or a variation, so it is about 40 Newton per millimeter square. If you have nickel cast iron, so I'm just going to say gray cast iron. If you have nickel cast iron, which is an additive, it's an alloy of cast iron, that can go up to 90 Newton per millimeter square. And if you have aluminum alloy, you can go up to 100 Newton per millimeter square. But I want to give you a word of caution. So these strengths are on the higher side. So it's always, if we want to be safe, we should select the strengths on the lower side. Because based on my experience, almost always the piston failure happens in the heat, not in the strength. So it's customary to sort of over design the piston based on the strength criteria. So for example, for gray cast iron, the lower value is about 30. For nickel cast iron, lower value is about 50 Newton per millimeter square. And for aluminum alloy, it's about 60 Newton per millimeter square. So here is something I want you to keep in mind. So typically, piston failure occurs in heat dissipation. So over design in strength is recommended. And again, it's a design problem. So there is always some trial and error back and forth that can go on. So let's look at the design based on the heat transfer. So for heat transfer, piston, it's considered flat plate. And equation for heat transfer because of flat plate is H divided by 12.5 multiplied by K, that is the thermal coefficient factor, Tc minus Te. So what is H? H is nothing but the heat that is absorbed by the piston. Heat absorbed by piston. And that heat has to be dissipated through the material. So value of K is dependent on the material. So for an example, for gray cast iron, it is 46 watts per meter degree Celsius for gray cast iron. For steel, it is 51 watts per meter degree Celsius. And for aluminum alloys, it's about 174 watts per meter degree Celsius. So this is for steel and this is for aluminum. Now, one thing, what is this TC and TE? So TC is the core temperature and TE is the edge temperature. So what do we mean by TC and TE? So TC is the temperature at the center of the piston and TE is the temperature at the edge of the piston. So, and here is the reason there is a relationship between these two, because if TE and TC, they are significantly different. So for an example, if TC minus TE is too high, that leads to piston warping. So you don't want the difference between the two temperatures to be very, very high. And I just want to give you sort of a rule of thumb. And that is typically when you are trying to design the core, the pistons. So you want to make sure you want to keep that temperature in the range of about 50 to 60 degrees. So this temperature, say between 50 to 60. Because if it's higher than that, then the material expansion would be uneven, and that would lead to localized stressing and then warping. Now, how do we find out the heat that is dissipated to the piston? And the heat that is dissipated to the piston is considered to be the fraction of the heat that is generated during the combustion process. So H is the heat dissipated, that is fraction, I'm going to call this K, of heat generated in combustion process. So how do we find out the heat generated in the combustion process? So heat generated in combustion process is coming from the burning of fuel, and calorific value is the amount of energy that fuel contains. There are two types of calorific values. One is a higher calorific value, which is called HCV, and the lower calorific value, which is called LCV. So heat generated is HCV, higher calorific value, multiplied by the mass of fuel that is burnt, multiplied by the brake power. So this is nothing but it's called as the mass of fuel that is used per brake power. So mass of fuel burned to generate 1 kilowatt of brake power. So this is also called as the brake specific fuel consumption. So M is brake specific fuel consumption. And that comes from the engine design specifications. The high calorific value, HCV, depending upon if you have gasoline or if you have diesel. So for diesel, it's about 45, 10 to the power 3 kilojoules per kg for diesel, and 47, 10 to the power 3 kilojoules per kg for gasoline. And again, this constant K usually is considered as the fraction, which is usually taken as 0.05. So what we are assuming is out of that heat that is generated, only about 5% of the heat is flowing through the piston crown. So what we can do is there are two ways to handle this problem. So we can design based on the strength criteria and check based on the heat dissipation criteria. Or we can design based on the heat dissipation criteria and check from the strength criteria. And both approaches are valid. But you have to work through a couple of problems to see which approach gives you a better result. So I would encourage you to look at the example, homework, and the quizzes to give you a little bit of familiarity on how to work out these problems. Now, if the piston thickness or the head thickness is very small, that is not good. If the thickness is too large, that is not good either. So what we want to do is we have to sort of optimize, and then we want to make sure that the system, the piston does not warp. So you can add ribs, internal ribs, to add to the strength of the piston. The next component, that is piston ring. So the next component is design of piston ring. So there are two types of rings. One is oil ring. So you have oil ring that actually scrape oil. That is the last ring. And then you have compression ring. That is actually sealing. So compression rings are usually made up with rectangular cross section, and the diameter is slightly over the piston bore diameter. And as we discussed in last class, there is a cut. So what you do is when you are putting the ring inside the piston, you actually slide it, and then when you drop the piston in the cylinder assembly, you have a special tool that compresses the ring, and then you slide the piston inside the cylinder and use it to make sure that the contact and the assembly is proper. So for the ring, the radial thickness T1 is called as the radial thickness of ring is given as D square root of 3 PW divided by sigma T. Again, this is the same stress that is coming from the bending of the ring due to the gas pressure. So just to give you some values here, D is the bore diameter, then PW is the gas pressure on the cylinder wall. So gas pressure, and this is slightly different because this is the pressure that is acting on the cylinder wall and the interface, which is about 0.2, 0.025. So 0.025 Newton per millimeter square to 0.042 Newton per millimeter square. Sigma T is 85 to 110 Newton per millimeter square. And the next thing is axial thickness. So let me give you how the ring looks like. So if you look at the piston ring, it's going to look like something like this. And you have radial thickness, and then you have axial thickness. So axial thickness is usually, so TR, TA is 0.7 times TR. And then there are some standard dimensions. So you have width of top land, and width of the top land is typically about the thickness, and the width of the ring band is usually about TA. And what you want to do is you want to make sure that these dimensions actually make sense when you're actually creating the CAD geometry. Because some of these dimensions, for example, these dimensions are based on the kind sort of the geometric consideration rather than the strength consideration. So for some reason, if you think the geometrical constraints are not satisfied, then you are welcome to change these dimensions within the prescribed guidelines. So next part is design of piston barrel. And in the design of piston barrel, you have thickness, which is about 0.03 Piston barrel design is completely based on empirical relations. Plus B plus 4.5, and B is nothing but the width of the land, um, which can be considered as about clearance plus the radial thickness, and then this information, and then you have piston wall thickness, and that piston wall thickness is again the same empirical relationship, 0.03 times D plus T R plus about 5 millimeter. So with that, the dimensions that we need to construct the CAD geometry for the piston is done. The last couple of parts of the piston are, one is piston pin. So design of piston pin. And the purpose of the piston pin is to hold piston and connecting rod together. So if you look at the piston, then you have this pin that kind of fits over here. And on the other side of the pin, you have connecting rod. So for design of pin, you can have a full floating or semi floating pin. So basically, in the case of full floating pin, the piston pin has little bit of axial movement. In semi floating pin, so basically you have one side constrained and the other side is allowed to move. So typical piston pin design is exactly same. This is same as bearing pin design. Or if you look at the pin design of knuckle joint. So the design principles are exactly same. So if you look at the total force is nothing but pi by 4 times d square multiplied by the maximum pressure. So this is the bore diameter, and this is the max pressure. And now what we want to do is we want to find out the moment, and that moment is given by the equation, and I'm gonna give you sort of an approximate equation without deriving it, which is force times diameter, bore diameter divided by 8. So let me, this is an approximate relationship, F times D divided by 8. And where does this approximate relationship come from? Is if you think about the loads or the loading pattern that we talked about on the pin, that has the forces that are uniformly varying and the forces that are uniformly distributed. So if you look at the bending moment with all the geometry, that approximately comes around force times D divided by 8. And once you have that, you have to find out, you have to look at the bending stress. Sigma T is equal to M divided by I multiplied by Y. Sigma T is equal to M. It's a circular pin, and typically the pins are hollow. So you have outer diameter and you have the inner diameter. So you have a hollow pin, and inside diameter DI is usually 0.6 times DO. So if this is DO, the DI is 0.6 times DO. So I is pi by 64, D outside to the power 4, T inside to the power 4 multiplied by T outside by 2. And the only unknown in this equation is DO. So we should be able to find out. And depending upon the pin material, you can have anywhere between 80 to 140 Newton per millimeter square as the bending stress. And you can use the piston pin is like a case hardened carbon steel, or you can use the alloy steel. So typical materials are, you use alloy steel or case hardened steel. Why do we use case hardened steel? Because the pin is subjected to high surface loads and high surface stresses. That's why we want that pin to be case hardened. Okay, so any questions on the piston design? So I would like to work out a problem real quick. But again, what I'm going to do is, the procedure is the straightforward same recipe that I just gave you. Let's work out a problem real quick. So design a piston. So piston design. And it's an older piston. So they are saying it's a cast iron piston. It's a single acting 4-stroke. And for this, the bore is given, so 100 millimeter. So what could happen is, it could be a complete design. So you will first design the cylinder, then design the piston, and so on. Or it could be sort of, they have designed the piston and they have designed the cylinder, and now you want to design the piston for the cylinder. So D is 100 millimeter, stroke is 125 millimeter, maximum gas pressure, P max. This is 9 times the indicated mean effective pressure, is 5 Newton per millimeter square. And you won't believe that if you add a turbocharger, this pressure goes by 1 or 2 Newtons per millimeter square. That could cause significant stresses in the piston and the cylinder. So IMEP, indicated mean effective pressure, is 0.75 Newton per millimeter square. Efficiency mechanical is equal to 80%, and the brake specific fuel consumption per hour, so BSFC per hour, brake specific fuel consumption per hour, which means the amount of fuel consumed per hour to generate 1 kilowatt of brake horsepower, is 0.15 kilogram. And the calorific value, HCV, is 42 10 to the power 3 kilojoules per kg. Speed is 2000 RPM. Now, first and foremost, we have to design. So step one, we have to design the piston head or crown. So TH is equal to 3P T square 16 sigma T, which is 3 times 5 times 100 square divided by 16. And I'm going to assume the value of sigma T as 35. So this approximately comes about 16 millimeter. It's a 4-stroke engine. So which means the effective strokes per minute are 2000 divided by 1, that is 1000. So N divided by 2 is equal to small n, that is 1000. And then what I'm going to do is I'm going to use the equation for indicated power is equal to PM times A times L times N divided by 60 to find out the indicated power. So this is IMEP 0.75 times area, pi by 4 100 square multiplied by 125 multiplied by 1000 divided by 60. And the reason I need to do this because the brake horsepower is not directly given. So this is 12.3 kilowatts. And from here, I can find out the brake power is indicated power multiplied by efficiency mechanical, which is 12.3 multiplied by 0.8. So with that, I should be able to find out the heat generated. So this gives me about 10 kilowatts. So I can find out the heat generated. H is equal to C times calorific value multiplied by the mass flow rate multiplied by the brake power. So this brake power is needed here. C is 0.05. It's 42 10 to the power 3, 0.15. And please note this power, this mass is in 1 hour. So I need to convert that in 1 second multiplied by the brake horsepower, which is 10 kilowatts. That gives me about 850 watts of heat that needs to be dissipated. So I'm going to find out the value of TH from the heat dissipation characteristics. H divided by 12.5 multiplied by K multiplied by TC minus TE. So 850 divided by 12.5 multiplied by the value of K, and you can choose the value of K for cast iron, which is 45, and this is about 60 degrees. If I want to say, this comes about 20 millimeters. So now we have a choice. We have 16 millimeters and we have 20 millimeters. So to be safe, TH is equal to 20 millimeters. Now you will observe that the thickness of the, the piston head based on the heat dissipation characteristics is typically higher. The next thing is finding out the radial ribs, and these radial ribs are again just plug and chug, looking at the empirical dimension. So I'm gonna skip to the step 3, which is piston ring. Design piston ring, and the equation is T is equal to D 3 PW divided by sigma T, and 100 3 0.035 divided by sigma T. I'm assuming to be 90 degrees. And sigma 90 Newton per millimeter square, and this gives me about 4 millimeters. And with all this, so this is the most important dimension. And once you find out the value of T, which is the radial, you can find out TA, which is 0.7 times TR, and then other dimensions can be determined from empirical dimensions. Next thing is design of piston barrel. And these are from empirical dimensions. So a word of caution. So if you think about here, once you find out the radial thickness of ring, you can find TA, you can find width, you can find width of the ring band. Piston barrel, all the dimensions are typically given in terms of uh, the empirical dimensions. So I trust that you would be able to plug in the numbers and get the value. Design piston pin. And that is given as, first you have to find out the moment, which is F times D divided by 8. F is the maximum gas force, and that is the maximum pressure, which is 5 times pi by 4 times 100 square. And you know the value of D, 100. You can use the material for pin to be about 50 Newton per millimeter square. And you can use the equation sigma T is equal to M divided by I multiplied by Y, and then plug in the values of moment, value of I, as we talked about, pi by 64, D outside power 4 minus D inside power 4, and D outside multiplied by 0.6 is equal to D inside, and Y is equal to D outside divided by 2. Yes, to answer Daniel's question, if the bore diameter is not given, please understand you can find out the bore diameter from the information that is given to you. For an example, IMEP, and this is a good point, IMEP is given to you, then you know whether it's 4-stroke or 2-stroke engine. And then what you can do is, but what they will do in that case is they will give you the value of brake power or indicator power. So if the bore diameter is not given to you, you at least need brake power or indicator power to find out the bore diameter. So what I'm saying is essentially you will be solving the piston, the cylinder design problem first, and then you will move on to the piston design. And that is the next, actually the natural progression. So when you start designing the engine, first and foremost, design the cylinder, use cylinder dimension, design piston, use piston dimension, design connecting rod, use connecting rod, design crankshaft, and so on. Okay, so I would encourage you to work out the details. And if you look at the notes that are uploaded on the canvas, I have actually solved a piston design problem step by step. And there is also a video lecture that talks about the piston design problem step by step. I believe we have one more lesson left. So 21st would be the last lesson. And in last lesson, I would talk about the design of connecting rod and design of crankshaft. But please understand, I don't think design of connecting rod and design of crankshaft are part of the quizzes or the homework. So with the piston design and cylinder design that we studied today, you should be able to finish all the assignments that are assigned to you so far. And in the last class, we will look at some additional engine design components. We'll design some additional components for engine, and we will do sort of an overview and wrap up the course. Yeah, actually, all the quizzes are already posted on Canvas. So please take a look at it and please turn those in on time. So we have just one more lesson. If you have any questions, I would be happy to answer.